All right, so this portion of our chapter, continuing with circular motion, deals with Newton's universal law of gravitation, right? His universal law of gravitation. And so when we talk about Newton's universal law of gravitation, we're talking about how there is gravitational force between any two objects, and how things that are held in an orbit are held in their orbital path by gravity, right? Do you know what I mean when I say orbit? Right, the moon orbiting the earth orbiting the sun, right? All of these different things are in orbit, and they're placed in that orbit and held in the orbit based on the gravity between those two objects, okay? So we have to really kind of shift our focus to think about what gravity is and how gravity is really affected by certain variables, okay? So you don't have to write this part down just yet. I want to talk through a couple things. So Newton started wondering, right? He's a smart dude. He has his 3 laws of motion, right? The law of inertia, his net force and acceleration law, and his law of equal and opposite reactions, right? He's got 3 laws of motion. But he also started wondering, why does the moon stay in this circular path, right? The moon follows these phases. We see it orbiting the Earth at the same pattern every month, every year, all that kind of stuff, right? We see it. And so he wondered, why does it stay in this circular orbit around the Earth, right? Because the Earth's orbit around the sun is not particularly circular, right? It's more of an elliptical shape, kind of an oval shape, right? But the moon stays in this orbital path. The circular orbital path. He explored the magnitude of the gravitational force the Earth is exerting on the moon compared to the gravitational force exerted on the surface of the Earth. And he solved these ratios, and he did a lot of math and a lot of discovery about what these relationships and these ratios were, right? We're not going to dive into all the math he did in the discovery portion of this, but he came out with this conclusion that kind of defines the universal law of gravitation. And so I'm going to put it up here. I would like you to have this definition at least written down once in your notes so that you can see it and hear it and write it, okay? So I'm going to read it out loud so that we can hear it as we're going. So it says, every particle in the universe attracts every other particle in the universe. Okay, that's important. Attracts every other particle in the universe with a force that's proportional to the product of their masses and inversely proportional to the square of the distance between them. This force acts along the line joining the 2 particles. Okay, so this is kind of the defining description of what gravitational force is. The first thing was, it says every particle in the universe attracts every other particle. Okay? That's proportional to the masses of those particles. And so what that means is that every single particle in the Earth has a gravitational force between every other particle. So why don't we see things start moving together, right? We know what gravity does. It pulls things. So why don't we see, right, why aren't Annie and I sliding toward each other right now? What do you think?
Because the gravitational force to the ground is stronger.
Bingo. Nice, Sydney. The gravitational force between our particles and the ground is stronger, right? Why is that the case?
The mass of the Earth is bigger.
Yes, perfect. There is nothing on Earth that has a mass greater than the Earth itself, right? There's nothing on Earth that has a mass greater than the Earth itself. So that mass and the Earth is going to trump everything else that we want to do, right? Everything else is going to have a fractionally small gravitational force in comparison to the force between our particles and the Earth, right? So we don't see things randomly start coming together because the Earth's gravitational force is holding things in place, right? I think it's interesting because we really don't think about there being a gravitational force between me and my water bottle, right? Things don't just instantaneously start moving together, right? That's not what happens. There is a gravitational force between me and my water bottle, but it's not enough to put those things in motion. Okay? So the second part of the definition that I want to look at is that it says this force acts along the line joining the two particles. And so all that means is that when I've got two people and there's a gravitational force between them, right, it really is acting from the center of their mass. So if their center of their mass, probably, I don't know, somewhere along here, right? Center of mass. It's kind of like the vector center of that object, right? If I've got really heavy something on the bottom but really light on top, my center of mass is going to be a little bit lower, right? Or vice versa. So center of mass from person to person. The gravitational force between these two objects does not go to the ground first and then back, right? The gravitational force between them, if they were to spontaneously combine or slide toward each other, it would be in a straight line. Right? It's very simple. I think that's a common sense, right? I think all of you are like, well, duh, right? But I just want that has to be made clear is that if these two things were to spontaneously, slide together and be attracted to each other in that way, then they would slide together in a straight line. Just like when things fall, right? When things fall to the earth, they don't fall in a zigzag line, right? They fall straight down. That's because the line or the force between the earth and that object is a straight line. Okay, so now I'm going to give you a couple things here, most of which is your main equation, okay? This is some more stuff that Newton thought his process. You don't have to write that part down necessarily, but he did find that after comparing the radii, the gravitational force exerted by the earth on any object decreases as it moves further from the earth, right? That would make sense to us, right? As we get farther away from the surface of the earth, the force of gravity is decreasing on us. Agreed? Right? What's gravity on the moon? Do anyone know the value of gravity on the moon? What is it on the earth's surface? Yeah, 9.8, right? 9.8 meters per second squared is acceleration due to gravity. On the moon, it's 1.7 meters per second squared. Okay, so almost like a fifth of what it is on the earth. And that's just because we're farther away from the earth's core. So even on like Mount Everest, right? Think about this, the highest peak on the earth's surface, our gravitational force is not 9.8. It's like 9.77, right? It's very small, very slightly impacted, but not enough like you'd start floating when you get to the top of Mount Everest, right? We're not talking about a big enough difference there, but there is a slight difference. And then the same would be true as if we went into a deep canyon, right? I'm talking it's got to be deep, deep, deep. Right? If we went into a deep canyon below the center of the earth, our gravity would be a little bit greater than 9.8. Does that kind of make sense? As you move further away from the core of the earth, we're going to see that gravitational, that force really change. Okay? He also reasoned that the force of gravity must be proportional to both masses. If we're talking about the earth, then the mass of the earth is one of them, and then the mass of the object is the second one. If we're looking at the force of gravity, but just between two regular objects, not dealing with the earth, we would put in the mass of both of those objects. So if I was trying to find what's the small, tiny little gravitational force between me and my water bottle, I would use the mass of my water bottle and the mass of me, right? So here's our equation for the universal law of gravitation. This one definitely needs to go on your equation sheet. Maybe I would even write down that this is not just a force, it's a force of gravity, right? It's Fg. Okay, and then there's some variables here, right, that we're really not sure about yet. We know that M1 and M2 are the masses of the objects, but G is what is called the universal gravitational constant. And that's a value that you'll need to memorize, or we can store it in our calculator as well, right? 6.67 times 10 to the negative 11th. Okay? That's a value that's always going to be plugged in for big G. Okay, and then maybe I would go ahead and write here that it's Fg right there, not just force. It's actually the force of gravity. Right, R stands for the radius, and it needs to be measured in meters. You'll see here from the units on G that our radius has to be measured in meters, force is newtons, mass has to be kilograms. Right? In order for G to be true, in order for G to work, the units have to match that. Okay, so newtons, meters, and kilograms for our values. Okay? All right, it says a 50 kilogram person and a 75 kilogram person are sitting on a bench so that their centers are 50 centimeters apart. What's the magnitude of the gravitational force each exerts on the other? Okay, so let's talk about the ending to that question. It sounds more confusing than it is, right? Let's think about this. If the Earth is exerting a force of 100 newtons of gravitational force on me, then I'm obviously exerting that same exact force back on the Earth, right? It's Newton's third law that says for every force there's an equal and opposite. And so when it says we're looking at the force that each exerts on the other, that really doesn't change the way we're solving the problem, right? You don't have to divide it by 2. You don't have to do anything like that. We're just solving for Fg. Okay, so we'll use our equation Fg equals big G m1 m2 over r squared. Okay, we're solving for Fg, so I'm going to leave that. I'm just going to leave G right there, even though we know it's 6.67 times 10 to the negative 11th. Right? You can plug in that number if you want, or you can just write it as a G. M1 is 50, M2 is 75. And then what do we need to do with our radius here? It's going to have to be converted to meters. Okay, and then we're going to square that. Okay, I will tell you that so I don't have to, I'm sorry, are we okay with how these numbers got plugged in? Any questions with that? Okay, when I'm working this in my calculator, I don't like to have to replug things in. I just like to keep using the answer button and keep moving through it. So I start at the bottom. Okay, I'm really going to start at the bottom and work my way out. Okay, so in my calculator, I would start with 0.5 squared and hit enter. Then I would take parentheses 50 times 75 close parentheses divided by my answer from that, right? And that gives me 15,000, and then I'm going to take that times G. Right? Does that kind of make sense how I work that? I started at the bottom, divided by that answer, and then I multiplied it by G. That just helps me so I don't have to replug anything in, right? I'm not having to retype my answer. And I got 1.0 times 10 to the negative 6 newtons. Now let's look at this problem. It's going to ask us, really we're going to have to do it in a couple different steps, okay? It says the force of gravity between two masses was 14 newtons when they were 10 meters apart, okay? Then it says the distance between them changed and the force became 56 newtons. How far apart were they then? Okay, let's just brainstorm a little bit here. If my force of gravity between my two objects is increasing, are they getting closer together or farther apart? They're getting closer together, right? But we don't know what that ratio is. Okay? Would you take a guess? If it goes from 14 to 56, what do you think? How much closer are they getting? Right, do you have a guess or not really? Okay, so let's go ahead and solve that. It says Fg is equal to 14 newtons equals big G. We don't know M1 or M2, but we know that our radius is 10. Sorry. We do know that our radius is 10. They're 10 meters apart. That's considered our radius. We don't need to cut that in half, right? The distance between them is called our radius. All right? But what I want you to think about is that between the first scenario and the second scenario, are their masses changing? No. So we don't really care what M1 and M2 are, but we do care about what the product of those masses are, right? Because it's not going to change from part 1 to part 2. So we can solve for this M1, M2 as a whole, and then be able to use it in the second part of our problem to find that final distance. Does that part make sense? Okay, so let's go ahead and solve for that group of M1, M2. If I was going to solve the algebra, I would go ahead and divide over G first. So I'm going to go 14 divided by 6.67 times 10 to the negative 11. Excuse me. Okay, I'm going to go 14 divided by that. I'm going to hit enter. That gives me let's just round to 2.1, but I'm really going to keep it in my calculator. Times 10 to the 11th equals M1, M2 over 10 squared. So now if I want to get M1, M2 by itself, I'm going to do what? Multiply by 100. Right, I'm going to multiply by 10 squared, which I know is 100. And that gives me 2.1 times 10 to the 13th equals M1 times M2. Now, we don't really care how that mass is split up, right? It could be split equally. It could be split 75-25, right? We don't really care how it is because the mass product is still the same for scenario 1 and scenario 2. So now let's go ahead and look at our second part of it. It says the force now is 56 newtons, and we're solving for how far apart they are. Okay, so I'm going to go 56 equals G. And now for M1, M2, I'm going to plug in 2.1 times 10 to the 13th over R squared. All right, so I'll do 56 divided by G. And that gives me 8.4 roughly times 10 to the 11th. That equals 2.1 times 10 to the 13th over R squared. Okay, do you remember our shortcut here when our variable's on the bottom? Do you remember what we're doing there? We're going to switch them places. Okay, we're going to switch those two places. So when I do that, right, there's algebra that goes into that. When I do that, it ends up with R squared equals 2.1 times 10 to the 13th over 8.4 times 10 to the 11th. So now I can go ahead and do that math. That gives me 25 roughly when I do that math. And so then I'm going to have to take R squared, and I'll need to square root that. I don't know why I plugged that into my calculator, but I know that R now is 5 meters. Okay, so this chapter, like I said, is a lot of calculator work, right? It's a lot of being able to plug things into your calculator correctly, a lot of being able to use that scientific notation correctly. Are we using the E button on our calculator for scientific notation? I hope, right? That's going to make things a little bit easier, okay? What questions do we have about how we solved that one? So I want you to look at the relationship here. What happened to the radius from part 1 to part 2? It got cut in half. But the relationship between the force, 56 divided by 14 is 4. So my force increased by 4 when my radius decreased by half, right? That has to do with the squared function of that R, right? So it's not just a true relationship if radius gets cut in half. I'm sorry, maybe it's not a true reciprocal relationship, right? It's not just when radius gets cut in half, our force increases by 2. It's really, I don't know what the relationship would be called, right? There's another multiplier to that, and it has to deal with that square function. Right? Maybe it's an exponential, I don't really know. Okay, what questions do we have about solving that one? Okay, but it says, what's the force of gravity acting on a 2,000 kilogram spacecraft when it orbits 2 Earth's radii from the center? Okay. So here's a value for Earth's radius, right? The radius of the Earth always goes from the core of the Earth to its edge, right, to its surface. And that value is 6.38 times 10 to the 6th. Okay, so the radius of the Earth is something that I think you should have down, right? I think you should write it on your equation sheet. It'll be something that I give to you, but we'll use it enough that I think you'll be able to kind of memorize it. But it says that our object is orbiting 2 Earth's radii from the Earth's center. Okay, and so that distance again is 6.38 times 10 to the 6th. Right? So we're not just looking here at the radius from the surface of the Earth. When we do problems that involve the Earth, right, and involve looking at the gravitational force of an object between itself and the Earth, we're always going to look at our radius to be the distance from our object to the center of the Earth. Okay, so that's kind of important for us. Whenever we deal with objects that are dealing with Earth's mass, the radius that we're dealing with is from the object to the center of the Earth. Okay? So for anything that's on the surface of the Earth, the radius we would deal with would be just this. Right? But since we're dealing with an object that's orbiting out here, we've got to now have a radius that's 2 of those distances. Does that kind of make sense? Okay. So when we look at our equation, it would be FG equals big G times mass of the Earth, 5.98 times 10 to the 24th, right? Usually I'll give that to you, right? But I think it's a good one for you to memorize and be familiar with. Put it on your equation sheet. Times M2, which is 2,000 kilograms. That's the mass of our satellite or spacecraft, okay? Over the radius, okay? So now our radius is not just 6.38 times 10 to the 6th. It's 2 times 6.38 times 10 to the 6th, and then we square that whole term. Right, does that part make sense? You could also just add them to... you could... Sorry, I'm being lagging. Okay, you could also just add them together before you even plug it into the radius. I think we end up with 4,900 newtons, or something very close to that.
Wait, why is it
Right? Do I need to show the math for that, or do we feel okay with that? Okay, so we end up with 4,900 newtons, and that's enough to hold that object in its circular orbit.